Solwise carry a wide range of antennas for Wi-Fi, 3G and 4G mobile data applications. This short introduction should help the uninitiated make some sense of the types of antenna that we carry and explain some of the terms listed in the specifications for them. This should help you in making a selection to best meet your needs. In the following discussion we will talk about antennas radiating energy. In fact, antennas that are good at transmitting energy are always just as good at receiving energy. This means that whenever we talk about radiating, the same will be true for receiving. Although there are many different techniques used in the design of antennas, they all have the same purpose: to provide an efficient connection between a signal cable and the air or free space around the antenna. Real antennas come in two basic types, distinguished by their radiating pattern: omnidirectional and directional. We'll start by looking at directional antennas. An antenna generates gain by focusing signal that would otherwise radiate in unwanted directions towards the desired direction. As the gain increases, the beam gets stronger and narrower. We describe the gain of antenna in decibels. Each time the signal strength doubles, the gain in decibels increases by 3. But how can we describe the pattern of the beam? There are two ways to describe the radiation pattern. If we draw a graph of signal strength against direction, we get something like this. Directly ahead, which we'll think of as 0 degrees, we have a gain of 9 decibels. To the sides and behind, we have effectively no signal at all. We've drawn this as minus 9 decibels. The common way to provide this data is to wrap the graph up into a circle, hence polar diagrams. The diagram we've drawn here shows the radiation pattern in the horizontal plane. To fully describe the radiation pattern of an antenna, we also need to take the side view, called the elevation plane. An important point to note about polar diagrams is that, although they are the definitive reference for the directional properties of an antenna, you do need to look at them very closely to understand what they mean. It is often difficult to see the scale on the radial axis, i.e. the separation of the circles, and yet they are effectively meaningless without this information. Here at Solwise we do our best to provide polar diagrams for all our antennas, but we are always in the hands of our manufacturers in this regard. The second way of describing the radiation pattern of an antenna is to use beam widths. We can derive these from our polar patterns. It's pretty clear that we can describe an angle of coverage based on the shape of the pattern in our polar diagram. But where should the edges be? The convention is to place the edges of the beam at the point where the signal level has dropped to 1/2 of the peak level, i.e. the -3 dB point. For most antennas you will find beam widths listed for both horizontal and vertical planes. The second type of antenna radiating pattern is omnidirectional. In fact, this is something of a misnomer. It implies that the antenna radiates in all directions, which it does not. The omnidirectional antenna generates its gain by taking signal that would otherwise radiate into the sky or the ground and send it equally into a disk in the horizontal plane only. The thinner the disk, the higher the gain. Polar patterns can again be used to describe the antenna radiation pattern. The H-plane pattern should be close to a circle at the radius corresponding to its published gain, and the E-plane pattern should be two bulbs